Welcome to this virtual presentation titled Test Data Masking for Db2 on z/OS. My name is Kai, and I want to show you how to get masked Db2 data in your test environments. There are a number of things in this presentation that are quite specific to Db2 for z/OS, but there's also a lot of material that can easily be transferred to other database systems, so I hope this is also interesting for you if you mainly work with Db2 for LUW or even non-Db2 systems. The main part of this presentation will be about designing algorithms that can be used to mask personal information and replace it with fake but plausible data. We will also talk about masking data consistently, and that refers to not only foreign key consistency, but also to masking data repeatedly, masking the same data that has different representations, and masking data in different columns that somehow belong together. I will briefly show you what to avoid in terms of data masking, because some of the more naive strategies can actually impact your testing in a negative way. And finally, we will have a look at the performance of our algorithms and how we can integrate our data masking strategy into a typical test data management process. I think everyone agrees that data masking is something that everybody needs to do, because we all need to test business processes, vendor products, and homegrown applications. And to do testing, you need test data. Now, the perfect source of data is obviously your production environment, because that has all the real data and all the real edge cases that we need to process in real life. But you can't just grab a copy of the production data and start testing with it. There are regulations and laws all over the place that limit what production data can be used for, and testing is typically one of the things that, strictly speaking, you cannot use production data for. So you need to modify that data before you can start testing, and you need to do it in a way so that it's no longer possible to identify a real person by looking at the test data. By the way, even if you weren't required by law to mask test data, it is still a good idea to do it. Production data is a valuable asset, and one way to minimize the risk of data theft or data leaks is to not have real production data in your test environments. So you've made a decision that you want to implement data masking, but now when you look into the details, it can become discouraging real quick, because the database systems do not really offer any built-in solutions. You have to come up with your own masking strategies. When you start to implement data masking for your test environment, you will quickly see that there are certain requirements that the data has to satisfy after masking. Obviously, there should be no way that someone can figure out what the real data was just by looking at the masked data. This is the key requirement for data masking. We modify the data in order to get rid of personal information, so you should not be able to somehow determine the real names, real credit card numbers when you have the masked data in front of you. At the same time, the application has certain expectations as to what the data should look like. Table columns have a meaning, and not every value that you can possibly put in a column makes sense for an application that uses the data. Some data types, such as credit card numbers, have an internal structure, for example a check digit, so applications will usually do validity checks when processing these numbers, and they will produce errors if the masked data is not plausible. Sometimes data in different columns is related, but not by a formal RI. When you think of addresses, you usually have a street name and a house number, a postal code, a city name, and sometimes a state or a province name. And these different components of an address are stored in different table columns, but there is a hidden relationship between them, and applications can, in theory, check if an address is valid. And finally, if there are any formal database constraints, such as unique keys or foreign keys, naturally we must not violate those, or else the database will not allow us to insert the masked data into our target tables. One strategy that often comes to mind when people first think about data masking is to just replace sensitive information with null values or with constant dummy values such as XXX. But that's not a good strategy. It's not only that you can violate unique constraints. The main problem is that when you have the same value for all rows, then this column has zero variety, and that reduces the usefulness of your tests. If you run a test 1 million times and the data that is being processed is always the same, then the fact that the test was successful 1 million times does not really mean anything. Other simple strategies include shifting letters or digits. Db2 has built-in functions that you can use to shift letters around, and you can do the same for numeric data with some basic math. This masking strategy has two big problems. One, it is insecure. When you shift letters around and you look at a list of names, it usually doesn't take long to figure out which letter is which. And two, it is possible to end up with masked data that an application will consider invalid. A simple example is a credit card number. If you shift all the digits in the same way, then you will certainly end up with a credit card number where the check digit is invalid. And finally, sometimes people just replace sensitive information with random values. Apart from the fact that this will also give you lots of invalid values if there are any constraints on the data in a column, this strategy has a much bigger problem. The masking process should be repeatable. If a table in a test environment is refreshed, you typically want to do the masking in the exact same way as last time. The reason for that is that you want your tests to run under the same preconditions every time. If the data in the test tables changes every night, then your test results become less meaningful. Maybe you have a test that fails and you make a code change to fix it. You run the fixed code on the next day, but during the night the test table was refreshed and it now contains totally different data. You run the test again and it succeeds, but now you don't know if the problem was really fixed or if it has just become invisible because the random value that triggered the problem is now gone from the table. So now that we know the things that we shouldn't do, the obvious question is what masking algorithms should we use instead? We have made good experiences with a masking strategy that we call hash-based masking. With hash-based masking, the masked value for a column is always calculated based on an input value or seed. And in its simplest form, the seed can be the original column value, so you could generate a masked last name from the real last name. But the seed can be anything. You can calculate a last name based on a timestamp or based on a numeric ID or anything else really. This is because the algorithms used in hash-based masking can take any input value and hash it, which means they reduce it to a single number. Hash functions can take a last name as input and calculate a single integer based on that name. Or they can take a timestamp and calculate a single integer based on that timestamp. The nice thing is that these functions cannot be reversed. If you know that integer, you will not be able to figure out what the original last name or timestamp was. These functions are pure math. There is no randomness and there are no side effects. The same input value will always produce the same hash value, and different input values, even if they differ only a little bit, result in totally different hash values. With that hash value, you can then calculate a masked value, such as a new timestamp, or you can use it to look up data in a static lookup table. Mapping tables, where source values are directly mapped to target values, are an alternative to hash-based masking that can be useful in some situations, but you need to refresh the mapping tables periodically, and you need to make sure that nobody has access to them, otherwise it would be easy to reverse the masking. So let's have a closer look at hash-based masking. The name itself contains the word hash. You have probably heard this word before. For example, if you write Java programs, then you know that every object has a hash code. If you download big files, you may have verified the file integrity by checking the hash sum of that file. But what exactly is a hash, or to be specific, a hash function? Mathematically speaking, a function is a relation between two sets where every element of the first set is mapped exactly to one element of the second set. For hash functions, the first set is infinitely large. Every conceivable value can be processed. The second set, however, has a fixed size, for example, positive integer values in the 32-bit range. That is one example of a hash function. It accepts any value and it returns a positive integer number. And since Db2 can convert every data type to a character string, strictly speaking, we really only need one hash function for all data types. Whatever value we have, whether it's a string, a number, a timestamp, we can just convert it into a string and then use it as input for our hash function. In practice, it is useful to have two hash functions, one for numeric input values and one for everything else, and the reason for that is that working with numeric data is much faster than processing strings. Now, we will often have situations where we want the result of the hash function to be in a certain range because the positive 32-bit integers, which are the numbers from 1 to about 2 billion, are just too much to handle. But luckily, Db2 provides the mod function, so we can easily force our hash value to be in a certain range. What the mod function does is calculate a remainder, So if we have a very large number and we calculate that number mod 1000, the result will always be between 0 and 999, and that is incredibly useful. From the point of view of a programmer, a hash function has several very nice qualities. It is stateless, so there is no need to keep track of any results that have been calculated. That means no extra flat files and no staging tables with information about which value was masked in which way. It has no side effects. A previous function invocation does not affect the next invocation, and it does not affect anything else either. And it is re-entrant, so it can be called in multiple parallel threads without the need to do any kind of locking. But the hash function is only one component of our masking algorithm. We usually don't want to use the hashed value directly because it's essentially just an arbitrary integer. It's not random, it's calculated, but we usually need to do something with it, do some additional calculations to get the type of data that we need. In some cases, we can directly generate our masked data based on that integer alone using nothing but math. If this is the case, then our masking function basically takes an input value, hashes it, and then it performs some additional calculations and arrives at an output value, and that is the masked value that we can write into the tables in our test environment. Here are some examples of data that can be calculated using pure math. All plain numbers, obviously. This can include numeric ID columns. Things like social security numbers, which are also purely numeric. Socials have some constraints as to which numbers are valid and which ones are not, but this is easy to handle. License plate numbers and driver's license numbers. Now these are not purely numeric, but it's very easy to just store the letters from A to Z and the digits from 0 to 9 in a local array, and then pick any of the 36 possible values. Repeat until you have the correct number of characters. Essentially, everything that is pattern-based can be calculated as well, such as a customer number that consists of 5 digits and 3 letters, for example. Date and time values. Db2 can do date and time arithmetic, so this is extremely easy to do. Credit card numbers are also purely numeric. There are some constraints, such as the check digit. I have an example for that in just a moment. UUIDs. They're becoming popular for primary keys because they are unique even across databases and systems. So that covers a range of different data types, but there's something missing. As you may have guessed, in some cases it is just not possible to use only math to come up with a masked value. One example would be names. It is not possible to calculate a last name using just numbers. The same goes for postal addresses and for things like bank names and routing numbers. What we need in these cases is a list of known good values, and we'll call this list a lookup table. For example, we could have a lookup table with addresses that has 1 million rows, and each row has a valid address with street, zip code, city, and so on. To generate a masked value, we first hash our input, then we use the mod function to make sure we end up with a number between 1 and the number of rows in our lookup table, and finally we pick that row from the lookup table, and that's going to be our masked address. The contents of our lookup tables could be based on our real production data. For example, they could contain a list of all the last names that exist in the production customer table. The big difference to a mapping table is that the input value is not mapped directly to a masked value. Instead, there is always the hashing step that ensures that all possible input values always result in a valid last name. And of course, even by examining the lookup table, it is still not possible to tell which masked name resulted from which real name. Since hash functions accept an unlimited number of possible input values and will return a value from a finite set, they are by definition not collision-free. And this means that it can happen that 2 different input values are associated with the same masked value. For things like names, this is usually no problem. But if we want to use the masked value in a key column, it has to be unique. There is a solution, at least for integer values. There is a hashing algorithm for integer values that was conceived by well-known computer scientist Donald Knuth, and that algorithm can be made collision-free in the range of non-negative integers. So if you use integers in key columns, you can mask these if you make sure you apply the algorithm to the parent column and also to all child columns. The relationship between the entries in the tables will be preserved, because the same input values will always result in the same masked value. That was a quick overview about hash-based masking algorithms and how they work. But now we need to actually apply them to our tables, and there are a number of things that we need to consider. We know that all our masking functions require a seed value. We need to decide which value to use as seed. One obvious choice is to use the same column as input and output for our masking function. Because of the way the masking functions work, the same original last name will always result in the same masked last name. So in this example, everybody whose real last name is Miller will have the last name Black after masking. And this is something that may or may not be desired. For names, it is usually not a requirement. Even members of the same family do not necessarily share the same last name. However, for addresses, it may be different. It may be a requirement that all people that are on the same cell phone plan or insurance contract live at the same address. So in this case, we must make sure that people with the same real address end up with the same masked address. We do have another option though. We can generate a masked last name based on any other column, so we could use the ID column if we have one. If we do that, then people with the same real last name do not necessarily end up with the same masked name. What's nice about this approach is that we only need the ID and not the real last name to get the masked last name. Now imagine that this table is a parent table and there is a child table somewhere that references the ID column. When we process the child table, we may not have a column with the real last name, but we do have the column that stores the parent ID, so we are able to get the masked last name by looking at the data in the child table. And this can be useful because maybe we need the masked last name to build an email address, or maybe because the first letter of the last name appears in a customer number or an invoice number or something like that. This approach has another nice effect too. If we run the masking algorithm on the same table more than once, it will not change the masked names again, because in this case they are all derived from the ID and the ID did not change. Mathematicians call that idempotency, and it can be something that you want or don't want. And compare that to the last slide where the name Miller became Black. If you repeat the masking process, the input is now Black and it will change to something else. So in the real world, the data in our tables is not as neat and tidy as we would like it to be. First of all, our tables are not always normalized, and we will find many situations where the same information is stored in multiple different tables. This is redundant, of course, but maybe the database design has evolved over time, so redundant fields were introduced for performance reasons or something like that. Maybe the tables weren't even designed by you, but they came with a vendor application and there is nothing you can do about the table layout. Then we have things like typos. They happen. The same name can be stored in two different columns and it can be spelled slightly differently. It just happens. For somebody that looks at the data, it is usually clear that this is the same name but with a typo, or the name is written normally in one field and in all caps in another. But for Db2, and therefore for our masking functions, these differences are a big deal. If the input string for a masking function is just a little bit different, then the function will return a totally different masked name. This is how we designed it. To get the same results, you have to do things like convert everything to all uppercase, remove white space, and maybe even truncate fields to the shortest representation that is found anywhere in your database. For example, you may have to truncate the street name to 20 characters if anywhere in your database you have a character 20 field and the street name is actually truncated in there. If you have numeric data that is stored in a text field, then you should consider converting it to a real number before masking it. This will allow you to be consistent if the same number is stored somewhere else in an actual numeric field. Long text fields that allow users to enter free text can also be difficult, and there might not be a good way to extract, for example, the phone number. But fields like this are never used by Db2 in a foreign key relationship. They couldn't be used in that way if the contents differ between two tables. So you may be masking them in different ways, but at least you're not violating any database constraints in the process. Here are some examples that you will find in the real world. Look at the social, for example. In 3 of our 4 tables, the social is stored as 11 characters with leading zeros and with dashes that separate the digits. But in one table, the social is stored as an integer. Now, obviously, this is a completely different representation, But the social is often used as a key, maybe not formally by Db2, but by an application. So we have to make sure that after masking, the socials are still in their old format, but they have been replaced with the same new number in all four tables. Now in practice, this means that you have to do some string processing to convert the social that is stored as characters to a number, then mask it, and then format it so that it gets the dashes back. I have also seen things like date values stored as integers. Things like that usually come from legacy applications. Maybe back in the day, the data was stored in a vsem, and people simply used a numeric field, and when the data was migrated to Db2, the column was created as an integer so that the application could remain unchanged. You can see some other things in here, such as differences in capitalization, typos, and names, where in some cases the first and last name are stored in one column, and in other cases they're stored in two different columns. Now in these situations, it's a better idea to generate new names based on a common identity column, for example, if you have one. Otherwise, it could get really tricky to bring all these names to the same representation so that you can mask them in a consistent way. The bottom line is, we need to tidy up our data before we put it through our masking algorithms. We need to remove extra blanks, we may need to do some casting to different data types, and especially for strings, you may want to do what you might call string normalization. By that I mean remove not only spaces, but also dashes, periods, commas, basically all punctuation. If you have names that contain diacritics, it's a very common thing, for example in French or German names, then it's a good idea to remove them before masking. This ensures that if you have the same name in your database twice, and one has the accent over the letter E and one has not, they will become the same name after masking. Obviously, all this is only relevant if you derive the masked last name from the real last name. If you decide to generate a masked last name based on an ID column, then you don't have to worry about what's currently stored in the last name column or if there are any typos in it. String normalization has its limits. When you look at all the different ways to spell the name of the beautiful city of St. Louis, Missouri, that we have here on the right-hand side, do you think it would be possible to come up with an algorithm that brings all these different strings to one common representation? Probably not. So at this point, you can either use a different column as a seed, or you can simply live with the fact that after masking, you will get different city names. Strictly speaking, these are already different city names as far as Db2 and your application are concerned. Human beings can see that this is all referring to the same place, but you could never use this in a foreign key, for example, and if your application searches all records for St. Louis, it may not even find some of these. Next, let's shed some light on consistency. We have already mentioned consistency when it comes to masking tables that are in a foreign key relationship, but there is another form of consistency that I want to discuss now. It is very common that data in one column is related to data in another column, even if there is no foreign key involved. A perfect example are addresses. When you look at an address, you have a street name and a house number, a city name, a postal code, and a state, and maybe also a country. These parts of an address depend on each other. If an application checks addresses for plausibility, it is important that the zip code belongs to the city and it must not be in the wrong state. These are dependencies that Db2 does not know about, so from Db2's point of view, there is never a consistency problem, even if we fill these columns with garbage data. But applications might care. But we still want to mask addresses, because addresses are personal information and we cannot have the real addresses in our test environment. So we need to mask the columns that belong to the address. In this example, 4 columns if we ignore the country for a moment, so that we get addresses that are not the real ones, but they must be plausible addresses. Remember for a moment what's inside our lookup tables. If we look at the one for addresses, then there's of course an ID column that starts with 1 and just keeps counting upwards. Then we have 4 additional columns, and these columns are used for the components of our addresses. In every row there is one address that really exists, so the street is a street that really exists in that city, and the city matches the zip code, and so on. By the way, you could generate this lookup table from the real addresses that you have in your production database, and with the way our masking algorithms work, the addresses would get shuffled around, but you would still have the same geographical distribution, for example. But you can of course also use any list of addresses that you can find. This lookup table can provide good and consistent addresses if we use it correctly. If we go back to our example, we need to mask 4 different columns here. And let's assume that we already have a masking function that picks a street name from our lookup table, and one that picks a city name from our lookup table, and one for the state and one for the zip code. We can apply these functions to the columns of our address table, and as always, we need to make a decision what we are going to use as the seed value for our masking functions. A naive approach would be to use the original column value, so we would generate a new street name based on the original street name, and a new city name based on the original city name, and so on. But there is a problem with that approach. The 4 columns for street, city, state, and zip code contain different pieces of information. If we take the street name, 1100 Congress Avenue, that's a string, and the first thing that the masking function will do is calculate a hash number based on that string. For example, we could get 46,340 as our hash number. The next column contains the word Austin. That's a different string, and therefore the hash value would be totally different. In this example, it might be 103,873. And for the state and zip code, we get another 2 different hash numbers. The way the lookup tables are used is that the masking functions calculate a hash number, use the mod function to make sure the number is between 1 and the size of the lookup table, and then it picks that row from the lookup table and returns one component of the address. So for the street name, we would look into row 46,340 of the lookup table and use the street name that is stored there. And for the city, we would look into a different row and grab the city name. And the state and zip code come from different rows as well. So you can immediately see the problem here. All 4 functions return values that are valid street names, valid zip codes, and so on, but together they don't make sense. Hollywood Boulevard is a street that most certainly exists, but it is not in New York City. And New York City is not in Florida, and it certainly does not have a Chicago zip code. So the resulting address is not valid, and an application or a test case might not like that. Even if there is only very basic plausibility checking, it could be a problem that the zip code is in the wrong state. This is not only a problem for addresses. If you store bank account information in a database, then for example the name of the bank and the routing number must agree. And there are many other situations where we have such a hidden relationship between the columns of our tables that Db2 does not know anything about. So how do we solve this problem? By making sure that the 4 different masking functions that are used to modify the components of our address all use the same seed value. If our table has an identity column, that could be a good candidate for the seed. If it does not have an identity column, then maybe you can concatenate the street, city, zip code, and state and use that as a seed. For getting consistency, it doesn't really matter which columns you pick as long as you make sure that the same value is passed to all 4 masking functions. So to keep things simple in our little example here, we are going to use the ID column. We feed it into all 4 masking functions. Now with the same seed value, all 4 masking functions get the same intermediate result when they calculate the hash value. For example, it could be 18,925. So all 4 functions would look at row 18,925 of the lookup table and grab the street, city, zip code, and state from the same row, which is good because we know that every row contains a valid address. The result is that after masking, you have a totally different address in your table, but one that really exists. In this example, a place in Louisiana that you could really find on Google Maps. And like I said, even if the data in your lookup table comes from the addresses that you have in your real production tables, then the data is still masked because the addresses are shuffled around and a customer is no longer associated with his or her real address. Now let's look at some different types of data and see what we can do to mask them. For names and addresses, we already know that we need to grab values from a big list of names or a big list of addresses. We have a similar situation for banking information. The bank name and the routing number must come from a lookup table because there's just no way you could calculate that. The bank account number is a bit more difficult. Different banks have different rules how the account number must look. They may have different lengths, they may or may not have check digits, so it's really a bit tricky. In practice, however, Applications usually do not do validity checks on the account number, so what we can do is use some clever math to generate a masked account number that has the same number of digits as the real account number, and then we'll just use that. For email addresses, you usually want the email address to resemble the first and last name of a person. This is not mandatory, the email address does not have to contain the name, but it's a nice thing to have and it's easy to do. Just make sure that the seed that you use to mask the first name and last name is also available in the table where the email address is stored. An ID column is a perfect example. To get a masked email address, you can generate the first and last name and then simply add a domain name. For test data, the domain name example.com is available. This is a reserved domain name, so you can be sure that you don't accidentally generate the email address of a real person. Social security numbers are not too difficult either. Take a seed, for example the original social, and then apply our hash algorithm. Use the mod function to make sure the number does not have more than 9 digits, so in other words calculate the hash mod 1 billion. But there are a couple of restrictions. Not every social is valid. One of the rules says that none of the 3 groups of digits can be all 0. Another rule is that the area number cannot be 666 or start with a 9. But it's very easy to use some basic math to check if the generated number is valid or not. If it is, great, we're done. If we generated an invalid number, we simply add an offset, rehash, and check again. You usually don't need more than 2 or 3 iterations here. The good news is that the social is no longer tied to a location, so we don't have to worry about the area number lining up with the place of birth, for example. Credit card numbers look pretty random, but there are 2 things that we need to take into account. Number 1, the last digit of a credit card number is a check digit. It needs to be calculated based on the other digits. Fortunately, the algorithm is well documented. It's called the Loon algorithm. Interestingly, it's the same algorithm that is also used for the check digit in Canadian social insurance numbers and also for several other identification numbers. The second thing to consider is that the first 6 digits of a credit card number are called the IIN, which stands for Issuer Identification Number. They identify the bank that issued the card, and they also tell us if it's a Visa card, a MasterCard, Discover card, or American Express. So we usually want to leave them as they are. So what we do is, if we have a 16-digit credit card number, we keep the first 6 digits, calculate new values for the next 9 digits, and then we determine the final digit based on the Loon algorithm. So masking a credit card number has a certain complexity, but it's all numeric and it can be still pretty fast. Date values also need to be masked sometimes. Somebody's date of birth is certainly personal information. Essentially, dates are numeric, but we do want them to be in a certain range so that we don't end up with people born in 1847 in our test environments. If we know a minimum and maximum date, we can determine the number of days between these 2 dates, and now all the masking function has to do is take the input value, calculate a hash, use the mod function to get a number that is between 0 and the number of days, and then just add this to the start date. Db2 has built-in functions to do date and time calculations, so it is very easy to add a certain number of days to a date, and Db2 will take care of flipping over into the next month or year. Sometimes you will want the month and day to change, but not the year. And this could be important for the signing date of contracts or when people's age must not change. So in that case, just take January 1st of the original year and add between 0 and 365 days to that. The number you add is of course the result of hashing the input and using the mod function. These were some data types that you probably have in your Db2 tables. Now I'm sure there are others that we haven't looked at, but I hope that this gives you an idea that masking data is maybe not as hard as it seems. But whenever you choose to modify the data in a table using masking algorithms, always look at the application and what it will do with the data. Sometimes the personal information that we are trying to remove is crucial for an application or for a test. For example, if you change somebody's first or last name or the social, that should not really affect the outcome of a test. But if you change somebody's address, that can have consequences. Let's say you work with an insurance company. Many types of insurance have premiums that are based on a location. If you have flood insurance and you live in the Rocky Mountains, you will probably pay much less than somebody who is living in New Orleans. So if you change the address through data masking, calculations in your applications may not add up anymore, and that could affect the outcome of tests. In this scenario, you may want to put additional constraints on the masked addresses. So for example, it must be in the same zip code area. Now obviously, this makes the masking algorithms more complex and also slower. In some cases, the best choice may be not to mask the addresses at all, but when you do that, your test environment will still contain personal information, so you must tightly control who has access to it. And there's more. So far, we have looked at structured data, but what about large text fields? Any CRM application has a big comment field for each customer, and you can put just about anything in there. You will find phone numbers, email addresses, contact information for other people, and all kinds of stuff in these comment fields. How can you identify what's in there and what parts need to be masked? What about pictures that are maybe stored as LOBs? A picture of an invoice or a business card can contain tons of personal information, but how would you change that? XML columns are also becoming more popular. Now that is not unstructured data, but it can still be very difficult and time-consuming to parse all parts of an XML document and identify names, addresses, and other types of personal information. Maybe your database contains a reference to a file that is stored on a file server, so you only have the path to the file in Db2, but not the file itself. What can we do about that? The answer is, in these cases, the best thing to do is exactly what I told you not to do in the very beginning. Just replace it with constant dummy values. Use a piece of dummy text and put it in all comment fields. Use a dummy image of a black square and put it into that lob column that stores JPEG images. This is data that is never part of a foreign key relationship, and applications usually just use the data as it is, so you can get away with replacing it with the same dummy value everywhere. Now that we roughly know what our masking algorithms should look like, how do we actually implement them? Somebody needs to write code and create those lookup tables after all. Here's an idea. Implement your masking functions as user-defined functions in Db2. For a while now, Db2 has allowed you to write user-defined functions in the SQL-PL language. This means that your functions are written in a language that combines SQL with things like loops and if statements. Since you can easily use SQL statements inside the function, you have the contents of the lookup tables at your fingertips. Once created, the functions can be used in select statements. This allows you, for example, to use it in tools like DSN-TIAUL. Instead of selecting the table columns as they are, you apply your masking functions right inside the select statement, and DSN-TIAUL will pull masked data directly from your source tables. You can then use the load utility to load the data into tables in a test environment. This means that you will never have any flat files that contain unmasked data sitting in your ZOS file system, which is good, because if you had any flat files with real personal information in it, that would be another thing that you need to secure and control access to. UDFs that are written in SQL-PL can also be SIB eligible, but unfortunately, as of today, only when called through a DDF connection. A function that is written in SQL-PL lives entirely inside your Db2 subsystem. There is no external load module that you would need to create and maintain. When such a function is called, everything happens in the Db2 address space, so there is no task switching and no WLM environment is required. Here are some tips to improve the performance of your user-defined functions. In general, invoking a user-defined function has some overhead, so what I usually do is avoid having too many nested function calls. If one UDF calls another UDF, especially when it's done recursively, the performance can really suffer. For small UDFs that need to be called in many places, it may be better to just inline the code, even though that is not normally considered good practice in other programming languages. Casting data to other types is an expensive operation as well, so try to minimize that. In general, working with numeric data is much faster than working with character data, so prefer plain integers wherever you can. And finally, try to implement your user-defined functions as inline functions wherever possible. An inline function is a function where the body consists of a single return statement. The return statement can have complex case expressions and it can call other built-in functions and other user-defined functions, but it needs to be one single statement. Of course, this will not always be possible, but if it is, then you can get a so-called inline function if you restrict yourself to the function attributes that you see here in the bottom half of the slide. When executed, Db2 basically inlines the expression behind the return statement into the calling select statement, hence the name inline function. Technically, no function invocation takes place, and that improves the performance dramatically. During one of my tests, the very same algorithm took 90 seconds for 10 million invocations as a non-inline function, but only 20 seconds as an inline function. That's about the same time as 10 million invocations of built-in functions. One attribute is particularly interesting, called on null input. With this attribute, you tell Db2 that the function body needs to run even if one or more input parameters contain the null value. The alternative would be returns null on null input, which tells Db2 that if any of the parameters is null, the function does not need to run. Instead, Db2 can assume that the returned value will be null. Now, you would think that by telling Db2 that in some cases the function code need not run would actually help Db2 and make things faster, but it will actually make your function considerably slower. I found this very counterintuitive, but the thing is, when you say returns null on null input, the function does not qualify for being an inline function. Db2 will create a package for it. It can no longer inline the returned expression into the outer select statement, and that's what makes it so slow. As for the lookup tables, these are tables that are not processed sequentially. You will see a lot of random access here. I have made some tests with plain old tables that have a unique index on the ID column. I have tried putting the table into a hash-organized table space, and I have tried using indexes with include columns. Hash-organized table spaces are a little faster, but they are deprecated and can no longer be created when you move to Db2 version 12 function level 504. But it doesn't matter anyway, because indexes with include columns are even faster. You have to make sure that the number of levels that you have in your index is as low as possible. When you use include columns, you can avoid to access the table space entirely, but the index entries will become larger. And that's why you want to increase the index page size. This allows you to have more entries per page, and therefore it reduces the number of levels. I have done 10 million random lookups using an index with a 16K page size and include columns, and I have found that the performance was almost as good as doing sequential access. I think that's pretty impressive, especially when you consider that Db2 can do things like sequential prefetch when you iterate over all rows of a table in sequence. Db2 seems to be doing a pretty good job here, allowing you to get almost the same performance with random access as you do with sequential access. Now, I want to wrap things up by taking a step away from the actual algorithms and looking at test data management concepts as a whole. I mentioned once or twice that you usually refresh your test environments on a regular basis. And this raises the question, how do you integrate data masking into your existing test data management processes? It turns out that data masking is not a one-time project. I have been to Db2 shops where 10 years ago a big data masking project was done and people were still using the same test environment from back then. This is not a good idea. It's not only that the structures of your production tables evolve over time and the test tables may no longer be compatible. The problem is also that data in test tables can become stale if it contains state and timestamp values. If you have not refreshed your test environments in 10 years, then every customer, every contract, every due date has aged by that amount of time, and that can affect your tests. That's why you need to refresh your masked test environments, and you need to do it frequently. As a consequence, data masking should not be separated from your test data provisioning strategy. It should be one of its building blocks. Broadly speaking, you can add data masking to your test data management processes in 3 different ways. Many people have an environment that's a complete clone of the production environment, and test data is taken from that environment and copied into the actual test systems. One thing you can do is apply data masking to this clone of the production. Here's what this would look like. In this picture, the real production data is red and masked data is green. What we have is a production environment on the far left side. Then the environment next to it is a so-called pre-production. Next to that, we have two test environments. Now those could be two separate Db2 subsystems, for example. And on the right, we have test cases that run repeatedly using the data from the two test environments. The red arrow represents making a copy of unmasked data. Now in this case, this would be a cloning process that creates an exact copy of your production system and creates the pre-production. Initially, all the data in the pre-production looks exactly like the data in production. Nothing is masked. But now you want to apply data masking in this environment, and that's what the blue arrow is supposed to represent. After masking the pre-production, we get this picture. The pre-production now contains masked data, which is great because now we don't have to worry about data masking when we grab data from the pre-production and copy it into our test environments. The green arrows represent straight copies of masked data from one environment into another. And the green double-sided arrows, that's test cases working with the data in the test environments. In other words, the tests read data from these environments and they may also change data. Note that in this picture, we only have one environment that contains unmasked data, and that's the production environment. That's perfect. We also have one central point where we apply masking, so you have a single point of control. But maybe you don't have a pre-production environment, so you need to copy data directly from production into the test environments. Or there is a reason why you do not want to mask the pre-production environment. Of course, if you have a pre-production but it's not masked, then you need to have strict access controls because otherwise everybody could just see and grab unmasked data. Now, you still want masked data in your test environments, but what you now have to do is mask data every time it is copied from production or pre-production into any of the test environments. Here's what this would look like. The pre-production, like the production, is red because the data in there is not masked. The copy processes that take data from the pre-production and copy it into the two test environments are now blue, which means that data masking happens during these copy processes. Data masking is always much slower than making a straight copy. Notice that we now have two blue arrows where we used to have one. And if you have more than two test environments, maybe you have 10 of them, then data masking needs to be done 10 times. So we can leave our pre-production unmasked, but the price that we pay is that we now need to do data masking much more often. Of course, the amount of data that is copied from the pre-production into the test environments could be much smaller, so this might even things out. But you can also see that you no longer have a single point of control for data masking. You need to ensure that it is done in all the processes that take data from the pre-production environment. There is a third option that we have, and up until a few months ago, I would have said that it is the worst option and you never want to use it. But I have changed my mind recently, and in some cases it may be the right thing to do. I am talking about masking data upon access. You can create so-called column masks in Db2. These column masks are basically rules that tell Db2 that when a certain user fetches data from a table using a select statement, Db2 is not supposed to return the actual column contents, but something else instead. This something else is expressed through a piece of SQL. And if we have implemented our masking algorithms as user-defined functions in Db2, we can actually use them in Db2 column masks and make Db2 invoke our masking functions every time data from a table is selected. Here's what that would look like. We now have all environments colored in red because they all contain unmasked data. But whenever a test case fetches data from the tables in the two test environments, Db2 applies the column masks and therefore sends the data through our masking algorithms before returning it to the end user. You can see that we don't have one blue arrow or two blue arrows, but many blue arrows. There could be several millions of arrows because every time a row is fetched, it is first masked. If a test fetches the same row 10,000 times, we will mask the same data 10,000 times, and this can be very expensive. So when is this a good strategy? Assume you have a very large table that has several billions of rows. The tests cannot run without this table, but they only use a fraction of the rows, maybe a couple of thousand. In this situation, doing data masking upon access can be cheaper than masking every single row ahead of time. It may be a special case, but I have seen situations where masking a very large table can take a whole day and then only very few rows are actually needed. So the bottom line is, look at how the applications store data in your tables to determine what needs to be masked and how, but also look at how intensively the tables are used during testing, and maybe you can save a lot of time. This concludes the session. I hope I was able to give you some ideas on how you can implement data masking so that your test environments no longer have to use real production data and the risk of data leaks and data theft is minimized. Feel free to contact me by email if you have any questions or would like to learn how we can help you to do data masking in your environment. Thanks for watching.